The purpose of this video is to go over the things that we covered in the week 3 class to catch you up from being absent. So our agenda, first of all, we exchanged the papers. I collected the quiz and the homework and passed out the new materials. Second, we reviewed the experiments, the pendulum, and the water in cylinders, which we collected data for last time in class, and also the paragraph experiment, which you collected data and analyzed at home. And then the third aspect of the class was new material on interactions and forces, and that will be a separate video. First, we reviewed the pendulum experiment. Our research question was, how does the period of a pendulum depend on the length? Your data should have looked something like this, and just notice here that these error bars are scratched out because they really are much narrower than how I originally drew them. This is a review of how we identify the pattern in the data when we have a handmade graph. So choosing 2 points where the x-coordinate doubles, I picked 1 second and 2 seconds. So when the time was 1 second, when the period was 1 second, the length of the pendulum was 26 centimeters. And when the time was 2 seconds, the length of the pendulum was 100 centimeters. And so you can see here that as the x value doubles, the y value approximately quadruples, so that's evidence of the quadratic pattern. Next, we compared the mathematical models to look at what was the same and what was different for all the students in the class, and what we discovered was that everybody had a quadratic pattern, everybody had used the same units, and the constant was very close. There really weren't differences other than the variations in the constant. Part B, we tested the model with a very long pendulum of length 399 centimeters. And so now what I'd like you to do is pause the video and calculate using your model, using your equation, your mathematical model. Substitute this length of 399 centimeters and calculate what period your model is predicting that that pendulum would have. Okay, so pause the video and make your calculation. Okay, now that you have your calculation, I will tell you that we tested the pendulum with stopwatches and we measured the period and we got about 4.0, plus or minus 0.3 seconds. So if the range of your prediction, whatever you calculated, plus or minus 0.3 seconds, overlaps the range of the test results, then we would say that your model is confirmed. And what we found in class was that everybody's models were confirmed. Next, as a group, we discussed each of these questions, and I'm going to skip that right now in the video, but if you have any questions about any of your responses to these, let me know and we will go over those. And finally, a summary of the quadratic pattern. The quadratic pattern is that as the y variable equals a constant times the x variable squared, when x increases, y increases. You can see that on the graph. And specifically, when x doubles, this is trying to show that look how tall this variable is, and now this x is twice as tall, then the y variable quadruples. So this is supposed to be 4 times as tall as this one. And you can see that here at 1 second, it had some particular length, and then when the period was 2 seconds, the length was 4 times what it was here. For the pendulum, if the time of one swing is doubled, then the length is quadrupled. The second experiment we reviewed was water in cylinders. Our research question was, how does the height of the water depend on the radius of the cylinder? First, we compared the mathematical models, and we found that everybody had an inverse square relationship between the height and the radius. So height equals some constant divided by the radius squared. But the constants were a little different. So one of the things we considered was that different groups had different volumes of water, and so maybe the volume of water was related to the constant. Then we tested the model with a large cylinder, really more of a vase, had a radius of 5.5 centimeters, and students used their model to calculate what height they would predict for their particular amount of water that they had. So different groups had different predictions because they had used different amounts of water to do the experiment. And then we poured the water into the vase and measured the height and found that these ranges overlapped, and so the models were confirmed. Lastly, we discussed the results, and these are the questions that you already answered in your lab notebook. So once again, if you have questions or uncertainty about your responses to any of these, let me know and we can go over those together. So these were all the questions. I think I will say right here on number 5, what does the constant in the mathematical model represent about the physical situation? And I'll just talk through this, but let me know if you have questions. If you consider that water inside the cylinder, the water kind of forms its own cylinder. It's in a cylinder shape. And we know that the volume of a cylinder is pi r squared times height. Now, the variables that were constant up here in number 4 was the height times r squared. So for this model, the height times r squared is equal to the constant, that number that you have in your mathematical model. But the volume of a cylinder is equal to pi r squared times h. So if you divide both sides of that equation by pi, you would have volume divided by pi equals r squared times h. But r squared times h is equal to the constant. So that tells us that the constant must be equal to volume divided by pi. So now what I'd like you to do is look above your data table or in your data table, find the volume of water that you had when you did this experiment and divide it by pi. Okay, so find the volume of water you had. Maybe it was 97 milliliters or whatever. Take that number and divide it by pi, and then see how close is it to the constant in your mathematical model. It should be somewhat close. There's obviously some uncertainty in our experiment, but you should be able to see a resemblance there. Okay, this is an example of a specific model. Yours is probably different because your volume of water was probably different than the data from which this model was determined. But here's an example of a model for this experiment. And we talked about, when would this specific model be valid? Would this work and give accurate results for height for every value of radius from 0 all the way up to infinity? Probably not. So we talked about, is there a larger radius at which you don't think the model would predict correctly? And one thought was that due to surface tension and cohesion, I'm not even sure the right words, of liquids, when you get to a certain width, the water is just going to kind of puddle and not spread out anymore. And at that point, your model is not going to work anymore to give you an accurate height, because the height's just going to stay constant as the cylinder gets wider and wider. Another possible thought here is that the molecules of water can't spread out any more than a thickness of 1 molecule high. So at the point where all the molecules, if possible, if a liquid could even do this, could spread out to that level of just only being 1 molecule high, wider radii aren't going to help. And then in terms of a smaller radius, if the radius got smaller than the width of a specific one single water molecule, then the water wouldn't fit in the cylinder. So, and there's probably other issues with fluid dynamics, and that would also be a problem. But in a general way, it's good to think about the model and when realistically or theoretically might it apply and not apply. Then we generalize the model. To generalize the model, what you want to do is take out any numbers that were specific to your situation and write a model that would be true for anybody using any cylinder and any amount of water. So to generalize the model, we replace the constant, which was a number, with units, and we're going to replace that by another variable, or a variable with another value that doesn't depend on your volume. So we found that the constant was equal to volume divided by pi. And so that's what goes here. So write this in your lab notebook at the end of this experiment, that the generalized model is height of water equals volume divided by pi, all of that divided by radius squared. And this is the same thing here. Height equals volume divided by pi, and then there should be a division line here because this is an inverse square relationship divided by radius squared. So the validity of the general mathematical model now is asking when would this model be valid? So we want to think, does the container have to be a cylinder shape? Would a rectangular container work? And we concluded no, a rectangular container would not work. It'd have to be a cylinder to have this inverse square relationship between height and radius. We also talked about, doesn't matter what the material is. Could it be a solid cylinder, say of, like a wooden doweling cut to different lengths? So that we figured would work. We even thought material such as sand would work. So as long as it can take the shape of the container, and if it's particles, that the particle size is small enough compared to the radius of the container, then that would work. For example, if you were using something, let's see, if you were filling your cylinder with tennis balls, then it's going to be important that you're only using radii of container that are much larger than a tennis ball. Otherwise, it won't work so well. Okay, so that's about validity. And to summarize the inverse square model, we have y equals c over x squared. This is the general form. When x increases, y decreases. You can see that over here. And when x is doubled, y is quartered. Okay. And this diagram also shows that if you double the radius of the cylinder, so if you look at these two cylinders, the one on the right has twice the radius of the one on the left, then the height of the water will become 1/4 what it was before. So the height over here is 1/4 the height of the water over here. Okay, the third experiment, the paragraph experiment. Our research question was, how does the height of a paragraph depend on its width? At home, you took data for this, and I put the data table here of my measurements, not because my measurements are more correct, but so that you can quickly compare your data and see if it's close. If you see something that's way different, then there was probably a measurement mistake on your part or mine, and we should figure out what happened. So compare your data, pause the video to do that, and then go to the next slide when you're done. Then we compared the mathematical models to find out what was similar, what was different. We found that everybody had an inverse relationship for their model, and everybody had very similar constants. So it wasn't too much different. Here is an example. I think in class the constants were more around 70 and 71, but that's about what the range was that we had. Here's some sample data. In class, we tested the model with a paragraph of width 27 centimeters. And at home, you already, as part of the experiment wrap-up, have made a prediction of the height, what the height should be for that width of paragraph. And then in class, we measured the height of an actual paragraph of that width and found that these ranges overlapped, and so the model was confirmed. We then discussed the results, and the only one I'm going to mention here right now is, what does this represent about the physical situation? Here we generalized the model, and I'm not going to mention it right now, but talk to me and we'll see if you figured out what that constant represented. And this slide we discussed a little bit, how would the curve change if the area of the paragraph was larger? And if the paragraph area was larger, the curve would be up here. And the reason why is that for a certain width, there should be a variable name down here that says width. For a width of 10, a small paragraph would have a data point here because it would have a certain height, but a larger paragraph would have the data point here because the height would be greater. So all the points would be higher for every width. And then we talked about the slope and how we could explain the slope in detail. So the slope starts out, when the width is small, starts out very steep negative, very large negative number. And then as it goes along, it gets more shallow, so less negative. So you could say that the slope is increasing as the width increases. And then to explain it in detail, we want to look at equal changes in width. So I picked changes in width of 5 centimeters. So for example, as we have this width of 5 centimeters, the height of the paragraph changes. It decreases by 8 centimeters. As we increase the width another 5 centimeters, the height of the paragraph only changes by a decrease of 2.5 centimeters. As we change the width of the paragraph by another 5 centimeters, the height of the paragraph decreases by only 1 centimeter. So we see that as the width increases, for equal changes in width, the change in height, the decrease in height, decreases. For the paragraph, this doesn't really have a lot of significance, but we will find as we start to study motion that this slope and how that slope is changing starts to represent something real about the situation. This is an interesting graph here, interesting picture. If you look at this purple or the blue here, this data point here, when this paragraph had a width of about 5, it had a height right here. And interestingly, if we outline that, so going from the origin to the point on the curve, we can see that that actually represents the area of the paragraph, because the area of this rectangle would be width times height. And then here, the green one, we can see that this is the width also times the height. So each of these rectangles has the same area, and that's really another way of looking at why the curve has this shape. We also talked about the validity of the specific model, that it would have to be for that particular paragraph, that has that particular area, and in that particular font. And the pattern was inverse, so summary here. The general form of the inverse pattern is y equals c over x. When x increases, y decreases. Once again, you can see that. So that part right there is the same as for the inverse square. But when x doubles, now y is only halved. So it doesn't become a quarter of what it was, it only becomes a half of what it was. And for our example here, for the same text, if you double the width of the text, then the height will become half of what it was. And so this brings us back to what we talked about at the very first class. Physics is finding and using patterns in nature to deduce the past and predict the future. And we were able to use our models that we found for each experiment to make a prediction about something we had not already collected data on. And then we were able to test those predictions and find out that the model had accurately predicted. And so then we were able to compare that our wild guesses were nowhere close to as accurate as our data-based predictions.